Sorry for the delay. I think actually, well, let's make sure that it's shared, right? So this needs. AC presentation? Guess so. Transaction within sharing. Okay, good. So it's a great pleasure for me to introduce Professor Jeff Anderson. So Professor Anderson is a faculty member at Purdue Fort Wayne, in the Department of Mathematical Sciences. He's currently associate chair and professor of mathematics. He's held many other positions. More recently, chair of the Department of Chemistry, an expert in applied mathematics with applications to many areas. And today is gonna talk about an application of to some ecology problem, I would say. Specifically, we'll talk about shallow lake model stable of data, largely food webs. So thanks a lot for the time you're dedicating to this presentation.
Put this back
I think that's with the
full screen.
yeah. One inch.
That'll box out of there. All right. Well, thank you, Alessandro, for the kind of coming out. Appreciate coming out to the subjects of stabilizing the river. So, first off, I'd like to introduce my colleagues on the biology. At the top here is Mike DeLong out in his element there. That's probably out on the Mississippi. Our campus out there, research and curricular, for Midwest and kind of a natural place. I heard that knee surgery and one time was trying to get the band back together. And I've been talking about these stories since about 2003. It's a testament to how long it's. I think went on for about 20 years. Down at the bottom here is actually at the and another part of the team. Yeah, funding through data analysis. And at the time, we want to acknowledge a lot of. Let's see, I guess I'm not hooked up here. We'll flip through this, or do I use this one?
Maybe the not sure. Yeah, usually when it doesn't work, you just click on again on there.
Okay, very good. So the areas of the rivers that we're going to talk about today. Focusing on this section between Wabasha and Clinton, actually, this is the first beach of the river. This fact has quite a bit of just right above a great deal of time. Back and forth in here. The payroll is passing through the the engineer manages part of the 7 Jackson dams that are managed by the Louisville engineer. Now, the topic here, long-term environmental impact, Jackson dams that will be installed. Now, that's not the period goes back into the 1880s. Water dams were installed in the late 30s up in the upper Mississippi. Lower area goes back into the 1890s, holding back the river that goes through a lot of this history. You can imagine some boats, or flatboats, or keel boats, as they were called. History reports part of the time the Ohio in front of Cincinnati was actually about 11 inches. But the snags in these rivers just make it completely impassable. When canalization is essentially 29, and there's a picture of a drop down when not needed, and part of that was they wanted to be able to river whenever the water was high, and then these things could be called needed to stock enough water to make for an navigable channel. 1950. So when we talk about the upper Mississippi still retains a great deal of these complex backwaters and floodplain systems. Well, you do have areas where there are side channels, and that will become of interest in results. The lower Ohio has been more of a constrictor throughout the history of it. You have very backwater areas. It's essentially so many areas has been really by navigation modification, but so interesting. Now I'll switch over to a link model, and this is sort of my intuition look at this. Is to talk a little bit about background. Mike and Jim are the experts. And yet, what I want to glean out of this is the method, at least the intuition of the physical situation needed adaptations that turned out to be when you talk about a shallow lake model that came out actually state. You're talking about there's some other things. The other option, turned out in the front yard of our property, it's down about 13 feet, 6 feet. When we first moved into this, and what was a lot of oscillatoria, the price you pay maybe is that, but you can maintain clear water conditions. And so the idea here, which has really been looked at in a number of studies, Schaefer, Jepson, is this what's called a regime states. What's wrong with it? Now, even modern studies have brought this out. They're really a 2021 study that just appeared in Nature essentially argues studies that are really and goes ahead and lays out data. They don't need this assumption of alternative equilibrium, which for me identifies with the thing we tried to do back here. The other part is, in fact, Schaefer, along with colleague Van Ness, a little bit earlier, set up from one included there, and body of water you're looking at. Now, this network and you let the cells go. At least I hope to be some of this active work I've done, a little bit different application in mind. So, actual mathematics of these things, the shallow lake model, if you put an L in here, limited growth model, this does is replace this limited growth. In fact, the L here, you'd have L divided. Just let that depend upon some nonlinear term that has to do with nutrient lake model, and something else that, in fact, lowers this as the vegetation gets higher. So you've got this balance of vegetation nutrient level, and A is the water column, which here is algae. And the two forms of these turned out to really be workable with the data we were looking at. Not necessarily fit. You probably well know. You can claim what we got either a system of equations that gave us no results or things that Now, the key that we're going to get into is to look at equilibria of a parallel of this that we develop, and all you have to do is set this equal to 0, solve a little bit, there are your equilibria. And Schaefer had drawn some of these based on these choices. I'm not really sure how they went and concluded this because that's as to how these go, but they've got them correct. If you look at above or below this equilibrium curve, that is, you've got A very large, very small. If A is very large, that tells you negative equilibrium. Equilibrium is everything apart. Below, table. A little bit more on this can be useful to keep in mind. There is
Right, right. Large amount of nutrients and number of
this actually
one.
limits out.
Again, I would expect one day event and
I mean, the limiting case
yeah, reasonable.
in terms of applying this to the basically, I didn't see in all of those studies anything about experimental data. Statistical analysis or sort of occurs. So, the idea is, yeah, saturated. And so that's 0, and so everything. And uh, V our application. The idea behind this one is as n increases, this should somehow increase the population of morbidity is what you think. Based on that, just I'll actually go through a graph of this, so you'll see that a little bit. The interesting thing that this creates is what's often called a hysteresis. You can start with nutrients low. You've got some kind of bottom regime shift or the alternate state or threshold, if you like, that this predicts is as the nutrients eventually the whole system snaps up. And if you say, oh, excuse me, oh, whoops, now I shouldn't have allowed that to, now you try to back to the, you've not only got to reduce nutrients, but you've got to get all the way back. So replacing the conditions with a clear lake, you don't just get to reverse this nutrient, you have to actually increase it all the way back. So this lack of reversibility is one you see in a hysteresis. So associated with this is in those studies that I have. What's happening is not so much that the nutrient level is being reduced, but the vegetation reestablished. So the two alternates based upon this principle in the upper Mississippi in the day, what you do, water more like native conditions, so the level runs down, and as that level gets lower, sun can reach the vegetation reestablish. Or I'm going to not worry about nutrients, and you'll see that replaced with a water level. See it. Now, another piece that I have to get through to introduce this is the idea of stable isotopes. Carbon has a stable isotope. Nitrogen actually has measure these ratios. It's ratio mass spectrometer sent off of another study that I'll look at in Diego. I'm not sure where the find that out before. These are compared with a standard for carbon 13. It's PE for nitrogen, in fact, air. Measured in parts per thousand. And some important properties about this. Them for 20 and negative 30, depletion standard. And there are these words, benthic and pelagic. If you think about it, the shallow lake, what's on the bottom, what's in the column. And if you're looking at reliance upon benthic sources by the kind of consumer out here, you see the current increase in carbon ice ratio. More reliance on pelagic, you see this decrease. And out there, I've got one prominent in here. The importance of carbon for this study is that these pelagic other data points to come up. to get to
Just
this.
that. I'm asking questions because the terminology is not familiar.
Another piece about this is that where you get this carbon data, you can get it from samples. In fact, a push in the whole area. There you can get is another study that was to get this out of sort of the growing state of the art. I'll show you a graph for of fish that gave you the carbon isotope. So our data is going to come in the form of carbon stage height discharge. And I've got this on a hidden slide. I voted against. You know, you can't feel, but Mike was chasing around the entire Midwest. Only used where you could get complete stats. What year period these came in? Periods. We broke out into active horizontal. It's almost like I can sort of crossover thing. Our study actually focused, as it turned out, on vertebrates and mussels and used for that G of A. And snails by another study that there's long time integrators of what's actually in that water column. The bottom the difference. Stage height is got complete sets, median or mean daily, maximum. IO at 19. Only limiting situation here for our data. About an R program, and it may be the same thing. This came from environmental software called Primer. One place where what should we use for this mean? What were good choices? And Violin pointed out daily and mean minimum. It turned out I had actually gone and started plowing out models for all of the possible choices. It pretty much turned out probably the best in many ways. So really, again, you get another indication of some differences for Mississippi and starting to again anticipate what I'm going to use the replacements in that shallow lake model. It turns out mess up everything as it turns out when you're trying to approximate methods. So get rid of them, translate back, no sweat. You can already anticipate here also at least values for DADT. Data points here things that were available. Now, the question is, those probably intended to be sent to me. Jim is over in Kansas, but it turned because as he was plotting all of these extra model, everything's still this model uh, fundamentally in terms of quality, nor the results. The carbon. ABT really encoding this isotopes. The studies of the shallow lake. So I want to build a model with this. So looking at this, and you'll see that. Thank you for that question. That's good clarification. All right, now to the analysis. These get graphed. It's part calculus exercise. You need to graph this thing. Done that a few times. Graph this, which is essentially A times A plus H here. And what you get is this. Turns out P and H have to for that to work out. As something like H of A increases, this max actually situation, because as you're looking for intersection points of this, as N increases, these levels way up, they get close to. The only way I get intersection points that go from, okay, for low N, you have one intersection, for N somewhere intermediary, you get change from 2, 3. I go to a place where I've still got 3, eventually F will hit where it crosses that maximum and you only get. It's a graph, in fact, a graph of A versus N. You replace these values here with the corresponding values of N. This thing and there's the shape. So hopefully a little intuition there about what I want to see from A times V plus H models. I'm going to have to approximate. If I use V to be linear, for example, this is quadratic. There's no way that would come out. The only way you can do that, argue V would have to be quadratic, get something that's cubic. F of N is something that is increasing, it saturates, but rises, falls, sort of like a white cube type of behavior. About that you can look at. This is not easy to see by looking in H's, P's, and everything else. That could happen, but I have a data set. It either might be just of mathematical interest, something of use. I don't know which. All right, here's my adaptation as we were talking about. Is going to the changes in carbon-13. I said, there, take back the array, and then the dA dt will just be the vegetation. I'm going to replace with relative carbon-13 recorded in snails. And it's going to be my water stage. Already kind of tipped my hand that this G, I couldn't get these to match, full to the data. You can fit. And so what I'm thinking of are Taylor approximations. This one I wanted it to retain a nonlinear. If I go and put a quadratic in, say, well, a couple of times, and it's hard to say with what you've got is just a strange artifact of the way you did the model versus anything of importance. Yeah, some relationship between these and my element here, but the way I understood this is this will tell me a little bit more about what's on. This will tell me a little bit more about. And these are. So I'll get kind of an. So when they told me something about that, I was. Okay, so my V equal G of A is a slightly better fit than linear, but really tough. not all that deterred by this. Models class, and you can approximate growth rate. I can tell you that the search that's out there. This kind of thing. Thing that we do is just use mathematics. Things that I have. And probably divide out this A and look at it. Didn't make any difference. This kind of stuff. You get coefficients, and this is because we try to do approximation. Notation. L here is actually going to be this is got a negative incorporated, so it's going to be this thing. Capital L.
Oh, sorry. What's the mean?
This is the mean daily water level. In fact, I've only got 30. Guys overrun. And here's what happens. Here tips way for me. For example, take n equal 1.5, go up to here. Trying to find out where that value intersects the A V plus H curve. Intersects it twice down here about 20, like about 27, and probably about 31. Questions here. A increases, this curve goes up above. A too small. Don't get any choices for V, and there's a little dip right here, which will basically pinch in these two values. If you plot that and turn it sideways, the two values that end out here. There are a couple of values that I printed out. You keep extending the other aspect that occurs. You're looking at changes. And that occurs up here at 15.5. All this and produce half of this, except moving it over, I did everything. And my some of the dynamics pretty well. In fact, looking at things, I won't show you all the data. Box that's bold is a predicate. 1935. This box here was a period of time from 1940 to about 60, where the management had water levels current management standards very narrowly focused those managed stage heights. And what you see here is through time, the vertivores are tracking really is mathematically a stable equilibrium. And narrowness of that stage heights. Interesting for the piscivores, they were operating out here near a threshold. Moved their way up into a little tighter box. Now, this is actually all of 2005. And here is pre-65, which was probably river. And this has worked its way up on stable equilibrium. The interesting thing about this is this fish gill has stayed without a lot of change. Piscivores have moved their way up. Reliance. The UMR is increasing benthic. LOR is a different story altogether. These things was in fact calculated by earlier analysis. Dramatic change in benthic reliance, pre-dam, post-dam. You can see it here. Huge increase in both gills. Now, quickly here before I run out of time, I thought it would be other analyses that were out there. Rachel Bowes, good students to Jim's 2015, 2016. She's been doing carbon and nitrogen isotope extraction from amino acids. You can start to figure out a bit more about what's in the diet. Bacteria, fungus, terrestrial, how much sun they use, etc. And the intriguing thing about this is that they went and combined both invertebrates because they saw a significant on the food was out of state. And they didn't see an appreciable change of these fish gills. Some pretty dramatic change to eat. Damn to both. I didn't look at what's really benthic budget. Isotopes and changes pre-dam versus post-dam. For Mississippi or not. Now, this was a historical study at all as well, using almost the same kind of range of years and data sets, museum samples, and so forth. Now, if you take a snapshot in 2014, there was a study done on Allegheny River. This middle section called a free-flowing. Oh, damn, I think this is a hydrologically. Then you get to the lower section that goes into Pittsburgh, where Allegheny come together to form the Ohio. And here you've got what they call the impounded section, or a typical lock and dam area. And over 10,000 fish that they caught all the way. You can tell this is like a snapshot in time. And their analysis showed this free flowing section, which is the part that's not lock and dam, it's more of a, native situation. Increase in benthic, increase in pelagic by the fish in the lower section. The thing I found interesting about this is a study that was done, colleagues did this about 2001, cooling in Upper Mississippi. And they found out that had a lower Ohio cooling effect in the higher than the upper Mississippi. Systems operate like, and yet the upper water, channels and so forth, the river, are operated more. Herbivores stayed around increased benthic for upper Mississippi, whereas towards pelagic resources. So kind of another quantification of this. Wrap up. Actually doing a presentation. And I started to think about some of the early that was used at the time, 60 gigs in I've got a terabyte that can take the one I used to have. When we first started this, so licenses for these things. They were expensive. It seemed like every time we turned around, we had to go to the 1331. Remember, I grabbed an anaconda. All of this data, I don't know what I was doing way back up here. Me doing an
Excellent. Um, uh, um, so first thing is, yeah.
because it actually compares well with leading the shallow lake model to this. Somebody usually asks, well, what happened to that parameter? In fact, what got fed? Mathematics. It's just it's not going to give you these separated out. So what I've done here is kind of handheld closely. But yeah, and this is the great another bad something that could possibly going to put in parameters that we all know you can fit that.
And the other thing I thought about that could reach look like maybe with the previous what maybe keep going backward.
Oh, okay.
Yes, this one. So yeah, the issue is keeping that
Oh, out here?
right. So well on the small e side, you look like gamma function. So I'm wondering if a combination gamma function early on and linear later on fits better than just approximating it. And I guess that polynomially it's when one starts from this model. But there are things like I think which have exponential functions. So I'm just thinking that maybe something in a sense will solve the little biology.
Well, the scale is all wrong for I have one of these asymptotic arguments. We're sitting there smiling. So for A large, this is roughly linear. And the minute you say A large, they ask, like, well, how large? Oh, I don't know. And smile because say if it's going to be carbon 13, I don't know if I can get that graphic back up. I mean, there's a range of meaning here. And it sort of changed my thinking completely to, okay, if I don't get asymptotic behavior the way I want it, maybe that's not the worst thing. That's where and none of the data arguments are a thing that I went the wrong way. Sorry about that. Asymptotic arguments are when I talk asymptotic, we're thinking about 15 and
Good. Well, thanks a lot, Jeff.
thank you.
Awesome. But all the chemistry part, yes.